Hello and welcome to How to Math with Dr. Ian. Um, we are going to be looking at similarity and diagonalization today. So get ready to think about eigenvalues and eigenvectors. Here we go. The first thing that we're going to do is define what similarity is. And it's this squiggly line here. We're saying that A is similar to B, and that is defined as being flanked on either side. Here A is flanked on either side by P and the inverse of P. So P has to be an invertible matrix. We've done this kind of thing before. If you remember all the way back to when we were talking about transformations in the 2D plane, and we derived how to come up with a reflection transformation over just the general line y equals mx. Remember, I'm gonna have to draw in a very small space here. But the process went something like, we were given a line y equals mx, and let's say our P matrix was like the rotation matrix. In order to, come up with a rotation, say we were trying to, a reflection. We were trying to reflect a point across the line y equals mx. Our solution to that problem went, all right, we don't really know how to reflect that immediately, but if we rotate, there we go. If we rotate the line down to the x-axis, and we rotate the point down to the x-axis as well, then we reflect the point over the x-axis, and then we rotate everything back. In the end, we end up getting a reflected point on the other side of that line, y equals mx. So what I'm trying to say here is that P is acting like that rotation matrix where we rotated it down first. Then A is the reflection transformation. Then P inverse is that rotation that gets us back to where we were. So we have encountered something similar to this before. Okay. This little lemma talks about how similarity is an equivalence relation on square matrices. And an equivalence relation just means that we're able to kind of sort all of the matrices into different classes, kind of like, we would be able to sort all of the fractions out there. We would be able to sort them into classes that are equivalent fractions. So if we had all of the fractions laid out on, a table, we could start putting things, all the fractions that are equivalent to 1/2, 2/4, 3/6, 4/8. We could put all of those fractions in a pile, and that would be an equivalence class. So similarly here, with matrices, we're able to group them up into equivalence classes based on this equivalence relation. And all that this says is that, a matrix is similar to itself. I mean, you could flank it on both sides by the identity matrix, and that counts as a similarity transformation. Here, if one matrix is similar to another, then that matrix is similar to the first one. And then here is what's called a transitive property. We've got A going to B. Well, A is similar to B, and B is similar to C. Then A is similar to C. The math behind that will show up here. So yeah, number one is just the identity matrix. Number two would just be the inverse of, P and P inverse in the opposite order. And then for that third one, yes, there you can find a matrix that would be, yeah, similar on each side. You multiply the two. Anyways, that is, whoa, that is the definition of similarity. We're flanked on either side by a an invertible matrix. There we go. Okay, another definition. The trace of a matrix is just the sum of all of the diagonal entries. That's what that sum is. And this trace is going to be useful for us as we, continue to talk about stuff today. It's not all that interesting by itself, but yeah, thinking about adding two matrices together, all of the diagonal elements would be the sum of the diagonal elements in this kind of a case. This is the kind of thing works out. I guess probably the one that would be the most interesting to look at would be number 3 there, where we've got the trace of AB is equal to the trace of BA. Do recognize that A and B here are both n by n matrices, so they are square matrices. And those traces are the same because you end up doing the same dot products for those diagonal entries in the matrix, either way you cut it. Yeah, and the proofs of those are just manipulating sums. Go ahead and check it out if you want to. Here we are reminding you of the characteristic polynomial. The determinant of lambda I minus a is, how we phrased it before. X is standing in the place of lambda. X is an eigenvalue here. You could use it to find an eigenvalue. Here we've got, we're making a polynomial. Yes. Properties of similar matrices. I suppose these are important to look through. If we have two similar matrices, then their determinants will be equal, their ranks will be equal, the trace will be equal, the characteristic polynomials will be equal, and therefore they have the same eigenvalues. So this is one of the most important things about similar matrices, is that they have the same eigenvalues. That'll tell us a lot about which matrices which matrices are diagonalizable. So let's take a look at some of these proofs. The first one we're going to look at is, why would the determinant be the same in both cases? Well, what we can do is look at the determinant of B. We're going to say that B is P inverse P or AP. And remember that the determinant of P and the determinant of P inverse are inverses of themselves. So when you do that entire multiplication, things cancel out. And you're left with the determinant of B is the determinant of A. So that's cool. The rank also, in order to have an inverse, P has to be, a matrix of full rank, of rank n. And so when you multiply by a matrix of rank n, you're not going to change the rank of the matrices that you're using. So that's why number 2 works out. Number 3 is the trace part. And we do use the little trace of AB equaling the trace of BA thing here in that bottom line. But yeah, their traces are equal. Cool. Moving on. Oh, geez. Here, let me skip ahead to get rid of that confusing nonsense. Okay, number 4 was the characteristic polynomials of similar matrices are the same. And again, this has to, deal with some algebraic manipulation. All we're doing is just writing in how B was defined, using the properties of the determinant along the way to show that eventually the characteristic polynomial of B is the same thing as the characteristic polynomial of A if A and B are similar to each other. And that definitely means that the eigenvalues are the same because the eigenvalues are the roots of the characteristic polynomial. Cool. All right. Now we can precisely define when a matrix will be diagonalizable. That is if it is similar to a diagonal matrix. And again, we've looked at this before. We've already decomposed a matrix A into the decomposition PDP inverse. So it's not completely new, but we're now using new vocabulary, and hopefully we'll be understanding it in a little bit deeper manner. Yeah, and here, is just some more vocabulary. We're going to use this notation here for lambda eigenvector is just an eigenvector associated with lambda. Cool. Moving on. Here we have an example. -1 is an eigenvalue of A, and X is an eigenvector corresponding to that. That's pretty boring so far. Yep. Okay. So yeah, just to remind you, the eigenvalues are the roots of the characteristic polynomial. The eigenvectors are all of the, basically the basis of the null space of lambda I minus A. So yeah, that's solving the homogeneous equation there at the bottom. That is the null space of lambda I minus A. Cool. All right, here we have a lower triangular matrix, and we're asked to determine all the eigenvalues. If you remember back to taking determinants of lower triangular matrices are really nice. You just have to go down the diagonal, and it's the product of the diagonal. So actually, all of the eigenvalues are listed right there for you. That's how it works out. Yeah, we've got all the eigenvalues just listed there on the diagonal. It's really nice. So, computationally, a lot of matrix algorithms work to, if you're trying to decompose the matrix and understand kind of, its essential inner workings, a lot of matrix decompositions have you break down at least one of the matrices into a lower or upper triangular form. There's something called a QR decomposition where you break a matrix down into a rotation matrix and a lower triangular matrix. It's pretty cool for understanding what's going on, but that's for later, if at all. Maybe I'll talk about that when we do least squares. Here we go. We've got an n by n matrix. A is diagonalizable if and only if Rn has a basis of eigenvectors. Sure, we need n linearly independent eigenvectors. Cool. Yeah, this is fine. So yeah, this result we've already talked about, but now we're using the term basis. Okay, this is a nice result that is very convenient. We know immediately that a matrix with distinct eigenvalues is diagonalizable. So, I guess if all of the eigenvalues were different, then we'd know right away that the matrix is diagonalizable because, eigenvectors that correspond to different eigenvalues are necessarily linearly independent. And we can see that using some induction here. As a base case, we just look at the first eigenvalue or eigenvector, and that is a linearly independent set because it's not a zero vector. And then we make the inductive step or the inductive hypothesis here, basically using the it's drawn with my finger. Come on. Using the definition of linear independence here, we're setting it up so we're weighting all of the eigenvectors by some value t1 through tk plus 1. And here we do some fancy multiplication. We're multiplying by a on the left, and that gives us a bunch of different lambdas, but also going back to this first equation and multiplying by lambda k plus 1 gives us this other equation. Then subtracting 2 and 3 from each other gives us this equation, which basically boils down to, yes, all of the first k vectors are independent just by the inductive hypothesis. And that means that this would necessarily be 0. And that proves that, since lambda I and lambda k plus 1 are different, we get this result, and the only way, that this all works out is that if we've got linearly independent eigenvectors, we're good. Okay, but that result is definitely handy. Here we have a matrix with n distinct eigenvalues. It's definitely diagonalizable. Moving on. Here we have a matrix, has a characteristic polynomial, has different eigenvalues. Therefore, we don't even have to, do any more work. We don't have to find the eigenvectors. We can just say it's diagonalizable. We could find the eigenvectors, but we don't have to say it's diagonalizable. Okay, here's an interesting matrix. I made a GeoGebra thing for this one, so we're gonna dive in. So first, we're asked, is this matrix diagonalizable? It will be. First we take the determinant of a minus lambda I, or lambda I minus a, whichever way you like to do it, to get this characteristic polynomial. That means that we have an eigenvalue of 2 here, and then we've got a repeated eigenvalue of -1 here. This kind of repetition is called algebraic multiplicity. Multiplicity. Because it shows up in the characteristic polynomial, we call it algebraic. And there is another type of multiplicity called geometric multiplicity. And that is the number of linearly independent eigenvectors that we get corresponding to a given eigenvalue. And so we're going to be able to diagonalize this matrix if the geometric multiplicity matches the algebraic multiplicity. Or in other words, we're going to be able to diagonalize this matrix if we can find enough linearly independent eigenvectors, within each eigenspace corresponding to the different eigenvalues. So basically, -1 is repeated twice. That means we need to find 2 eigenvectors corresponding to that in order to be diagonalizable. And indeed, we do find two linearly independent eigenvectors. And so this matrix is diagonalizable, even though it wasn't guaranteed to be diagonalizable just based off of the eigenvalues, because we did have a repetition here. Now, I promised you GeoGebra. Hopefully this is going to work. Yes. Okay. I know this is a lot. So, what are we looking at here? Well, we've got our just our standard basis vectors there in red, blue, and green along the x, y, and z axis. We also have the three eigenvectors for this matrix that we were just looking at. Those eigenvectors happen to be, x1, x2, and x3 here. And I've got those in black. I have one eigenspace corresponding to lambda equals 2 in orange. That's going to be that line. And when I play this transformation, you should watch that line, and that line will stretch out by a factor of 2. And then this plane of pink dots is the eigenspace determined by the eigenvectors corresponding to lambda equals -1, that repeated eigenvalue that we had. So the repeated eigenvalue actually, maps out, spans an entire plane. And when I play this transformation, watch how those two eigenvectors end up pointing in the opposite direction of where they were, but they stay in that same plane. And just overall, maybe I don't know, try to do this from a couple of different angles, but just there's little tiny blue dots all through this. They're arranged in just a square lattice, and I know it's a lot to look at, but I put those there just so that you could get a sense of how all of space tends to, either move towards or kind of move away from these eigenspaces. They're very important to the overall transformation. So, without further ado, let's play this and see what happens. Watch both of those eigenspaces. The orange line stretching out. The pink plane is flipping over on itself. And all of space kind of followed suit. So yeah, you can see here that the eigenvectors stayed in their own eigenspaces, whereas the standard basis vectors are kind of in this, I don't know, triangular kind of orientation where they've definitely been knocked off of where they used to be. But yeah, I think that that's really cool. I don't know, let's try to watch this from another angle. All right, now we're back to the beginning. See what happens. Nice. So yeah, this is available to you. Look at our GeoGebra demonstrations link on Canvas. This one's labeled 5.5 2D eigenspaces or something like that. Yeah, so have fun playing around with that. Back to the slides. Okay, so we're diagonalizable here. All of the algebraic multiplicities line up with the geometric multiplicities, and we're good. Do I even want to talk about this one? This is technical. I don't know that it will actually be that useful for us. Um, what this says is that we have a matrix A. It has k linearly independent eigenvectors. And what we're going to do is ex- extend, or we're going to add to that we're going to add to that set of vectors, that set of k vectors, a few more vectors, so that we get up to n linearly independent eigenvectors, or just vectors in this case, enough so that it is a basis of Rn. And we will make that our eigenvector matrix P. Yeah. And so if we had eigenvalues corresponding to the eigenvectors x1 through xk, then P inverse looks like this. This is, I don't know. This is extending an eigenbasis onto a basis for the whole space. These are, basically, block matrices here. Yeah, honestly, not that important. But now we've looked at it. I'm not going to look at that. I'll pause real quick in case you want to pause and look at it. Boom. Okay, we've got eigenspaces, and I've been using that language, but the eigenspace is just the span of the eigenvectors that correspond to a given eigenvalue. And definitely, each eigenspace is a subspace of Rn because each eigenspace is the null space of a matrix. Remember, it's the null space of lambda I minus A. And we've already shown that null spaces are subspaces. Proper. Okay, and here we're using the language of multiplicity again. Yes, this is the algebraic multiplicity, the number of times a given eigenvalue shows up in the characteristic polynomial. And this piece, this is the geometric multiplicity. This is the number of linearly independent eigenvectors. Linearly independent eigenvectors. And so always the algebraic multiplicity will be at least as big as the geometric multiplicity. If we're diagonalizable, those things are equal. But the case when we're not diagonalizable, we'd always have n eigenvalues, but we might not have enough eigenvectors to actually span the n-dimensional space. And that's when we're not diagonalizable. Yep. So this is exactly what I just said. This result tells us that if lambda is an eigenvalue of A, then the number of linearly independent lambda eigenvectors is never more than the multiplicity of lambda. Sure. Yeah, no. Definitely. We're going to be looking at diagonalizability. And I've said this already. When we have a matrix here, n by n, it is diagonalizable precisely when, for each eigenvalue of A, the geometric multiplicity, the dimension of the eigenspace, is equal to the multiplicity of lambda. So if the eigenvalue is repeated 3 times, we need to find 3 linearly independent eigenvectors associated with that eigenvalue. And here we go. We have another 3 by 3 matrix. This one won't be diagonalizable. When we calculate the characteristic polynomial, here we get an eigenvalue of 3 and another repeated eigenvalue of -1. So here's lambda equals 3. Here's lambda equals -1 twice. And so we know that we would be able to find an eigenvector for lambda equals 3. That's no problem. That is a distinct eigenvalue. But the repeated eigenvalue, -1, we have to work and see, do we have a two-dimensional eigenspace associated with that? And here, sadly, we only have one free variable, so we're only going to have one parameter. That means we're only going to have one vector in our parametric vector form of the solution here to this homogeneous system. That means, yeah, for this matrix, -I minus A, it only has a one-dimensional null space. And that's not big enough because lambda equals -1 is repeated twice. So this is not diagonalizable. Here we go. Two matrices. One of them is diagonalizable. The other one is not. If you end up going on to graduate school and studying matrices in more depth, this kind of a setup where you've got a couple of ones along the diagonal, 0 below, and a 1 up above in the top right corner, this is called a Jordan block, and it's one of the fundamental things that you'd be using to build up the Jordan canonical form, which is a kind of decomposition of a matrix based on eigenvalues and eigenvectors. So yeah, the fact that that thing is there means that I have a repeated eigenvalue of 1, but I know that my eigenspace is only going to be one-dimensional. And you could think about making a tiny augmented matrix for that, and that is rank 2, and therefore when you subtract 1 off the main diagonal, that matrix will be rank 1, and so the dimension of the null space is only one-dimensional. Whereas, yeah, we're good. I'm kind of getting sidetracked. But yeah, you'd see that B doesn't have enough linearly independent eigenvectors associated with lambda equals 1. Yeah, right there. And finally, we're going to go into a little foray here into some complex numbers. Maybe this is exciting for, electrical engineering people. We're not going to do too much with it, but we do have a fairly important result that, symmetric matrices have real eigenvalues. So we could take a look at this matrix and we could try to diagonalize it. We get a little bit of a weird characteristic polynomial, x squared minus 2x plus 2. And the only way to, solve for x there, we would find that, x is complex numbers. If you're using, say the quadratic formula, you would come up with 1 plus I and 1 minus I as your two complex eigenvalues. Do notice that those eigenvalues come in a complex conjugate pair. Complex conjugates behave in a way that if you multiply them together, the imaginary parts drop out. So yeah, that's a complex conjugate pair. That's not, an accident. That always happens whenever you're finding eigenvalues. If they are complex, they come in pairs. And there are some corresponding eigenvectors. So like if you're comfortable with using complex numbers, you can actually, find eigenvalue, eigenvector pairs, and it's completely fine to do stuff with complex. And that's, happening here because we have that -1 here and the +1 over here. This is not a very symmetric matrix. Those parts are opposites of one another. Let's keep going. So yeah, there's a diagonalizing matrix for A. Cool. Yeah. Okay, here's the theorem. The eigenvalues of any real symmetric matrix are real. So when you're working with a symmetric matrix, eigenvalues are real. The only way you get complex eigenvalues is if you're not symmetric. And this proof is not super important to fully understand, so we'll go through it somewhat quickly. Here we have x, which is an eigenvector corresponding to lambda of the matrix A. Do note that since we're working with a real matrix A, the complex conjugate of that matrix is the same as the matrix is before. You get a complex conjugate by negating the imaginary part. And so we look at this, eigenvalue eigenvector equation, ax equals lambda x, and look at the dot product. Well, it's kind of a dot product. You're taking the dot product with x and its complex conjugate. What do you call that? Ooh. I feel like there's a special name. Anyways, I mean, for this, I know that we would be, if we're looking at x as, a complex valued vector, this really is finding the length of that vector in a, complex context. Notice that when you multiply a complex number by its conjugate, we're still getting the length of this vector squared, like you would kind of expect to do when you take the dot product of a vector with itself, just in real number context. Anyways, going through some fancy algebra here, where we do make use of the fact that A is symmetric and the matrix A is real, so it's the same thing as its conjugate. We can show that, this value, which is really kind of the length of the vector x squared, that is in this process both times, but we're able to show that since lambda c is equal to the conjugate of lambda c, that lambda equals its own conjugate, and that means that lambda's real. I don't know. That's fine. Anyways, the big things that we talked about today were similarity. We know that similar matrices have the same eigenvalues. We talked about the trace. We talked about that a matrix with n distinct eigenvalues has n linearly independent eigenvectors and therefore would have a basis for the entire space. We looked at, you know, the eigenspaces for a certain matrix in GeoGebra, and then we looked at symmetric matrices real quick here at the end. If you made it this far, thank you for listening. I hope you have a great day. Check in on Pronto if you have any questions, and I will see you in the next one.